Okay, so today is the chapter 11. So it is actually spatial point pattern analysis, which is the kind of another one of the very important spatial data analysis technique. So whenever you have a points, actually there is a kind of a two attribute, because one is the point characteristic by itself, like an attribute, and also point location. And also maybe the other thing that I can also talk about is the distribution of the point, like a point pattern. So point pattern analysis actually allows us to explore those kind of I would say about the underlying mechanism of the points being located and the intensity of point, and then what's the distribution of the point are related to the other external factors or variables. So as you can see here, it is actually concerned with describing the pattern of the points. So whenever you have these kind of randomized points, there might have some of the pattern, like maybe if there is a lot of clustering nearby this area, that is definitely kind of, I would say, about the pattern. So when we try to describing or analyzing the pattern, and then what is I would say is the variation of the intensity of the points, we actually using these kind of a point pattern analysis. And then it is also inferential statistic to generating the observed pattern should be generated, and then the main focus is the kind of a location of the points, and then how those things are distributed. So it is actually example about some of the accidents or disease cases. Actually, I actually use the spatial point pattern analysis for my peer review journal publication. At that time, I actually using the location of the evicted housing, like housing evictions. There is actually location point. I actually geocoding these kind of points, and then there is definitely have a pattern. And then based on that, I just try to analyzing how those pattern can be variation of those point location can be explained by the other like external variable. So that's the kind of a point pattern is about. So it is also all kind of locations and also estimating the value of the observed phenomenon. And then it is actually, I would say, about the how those things gonna be generated. So that means point pattern analysis actually focusing on the kind of estimating the probability of the points being generated across space, or maybe across our study area. Okay, so that's the kind of thing. So whenever you have a kind of some kind of a polygon boundary, and then there is actually points, and then maybe you can see later there might be definitely have some kind of a heat map type of the plots, and then based on these kind of density or intensity of the points or probability of the points being generated, this gonna be the main focus of the spatial point analysis, like estimating the likelihood the points, some random locations, probability of the points can be generated across the random spaces. Like when I say about the spaces, that it is actually continuous space. So all of these within the boundary windows, all of these things is kind of it's a continuous spaces. We actually estimate about whenever we have a random locations based on our spatial point analysis and then a spatial point pattern model, we can actually estimate what the likelihood that points can be generated in that spot. That's how point pattern analysis is about. So in this chapter, actually, they actually using the SpacStat kind of packages, because a spatial package is one of the very important critical packages that allows us to especially explore the spatial point pattern analysis. And also in here, the author mentioned about the Bradley, Lubach, and Turner's book. This one. I'm actually wanted to show you about that book because that book is a very, very kind of a. Can you see my Amazon screenshot? Everyone can see
Amazon, yes, but not the book.
Yeah, yeah. So actually, so what I wanted to show you is this book. If anyone has an interest into the more understanding about what the spatial point pattern is, this book is the kind of a Bible for the spatial point pattern. And then this book actually have a very thick because it is 810 pages book. It's a lot of pages. And then it actually literally explain about everything about the spatial point pattern, how we can analyzing those things, and then how we can visualizing those spatial point pattern, and then how we can analyzing them. And then when we spatial point process model, I would say SPP model gonna be developed, how we can validate that model, or like a modeling diagnosis, like L functions, or like a L function kind of things, like a linear kind of a function of the Poisson point pattern process. So those things actually explain in here. Actually, I personally say about in chapter 11 of our textbook does not clearly explain about everything about the point pattern analysis because it's huge. They actually the authors try to summarize about what's the point pattern analysis from that book that I just mentioned. But I personally think that the author actually missed a lot of points. For example, like when we looking at the maybe this one does not show. Okay, here. When we looking at the table of contents of the data expressions and spacing, these are the kind of exploratory spatial data analysis point pattern. And then when it comes to the inferences, there's a lot of kind of a technique, like especially for the model validation part is definitely missing in our chapter, like how we can draw or calculate the L functions or G functions for the validation of our spatial point pattern model. But in here, actually, they actually try to summarize it very briefly about what the spatial point pattern is. So whenever you want to understand the spatial point analysis much further, I definitely recommend you to check out that book. It is very expensive. I actually bought that book because I really need it for my dissertation and my peer review journal article. Yeah. Yeah, Bruce and Comer also has a good second edition of the book, also has that chapter, but even that one does not include too much information about the spatial point pattern. This one is actually a kind of a Bible. Maybe I think that for your references, I particularly recommend you to check out the chapter 3 and 4 and 5. That is actually a brief introduction about how those things goes and then what the process look like. But anyway, so I'm gonna try to I'm gonna try to explain the spatial point pattern analysis based on our textbook, but I'm gonna try to add in a little bit more information if I get needed to. So here is the kind of chapter 11.1 is the observation window, which is a kind of whenever we creating the points like this, there's a definitely have a kind of a bounding window should be defined so that we can actually calculating about the intensity or density of the points as a kind of exploratory point analysis. So when we do not have any kind of boundary window is defined, that means actually the arbitrary kind of a point, arbitrary boundary window is defined based on the points, edge of the points, or maybe we can, as you can see at the bottom, you can, depending on the how we can how to define our boundary windows. Maybe this one is a 1 by 1, and this one is a 2 by 2. So depending on the what shape and then the scope, the area of the bounding observed bounding windows, it actually changing about the distribution or point pattern, exploratory point pattern characteristics gonna be the changes, as you can see here. So it's a kind of a 1 by 1 square. It's kind of a very seems to like a randomly distributed, but when we try to do the circular boundary window with the 2 by 2, it looks like it is actually clustering in here. So depending on the how you can what's the your boundary window, like what's the your boundary is, depending on your boundary, it actually the point pattern gonna be the vary, or how the way we understanding the point pattern gonna be different. Okay. And then the other way we can also estimating about the density is what is called the quadrat count, which is based, as you can see here, in case of the square, we can actually dividing about the very uniform unit grid like this, 3 by 3, and then we just counting it within how many points in there inside this each unit grid. That's how we can understanding about the pattern, or especially for the intensity of the points, depending on our unit grid. Okay, so like here it is actually 4 points inside the square, so you can say about the 4, and there is actually 1 is the 1 like this, and also same for the square. So whenever we have a square, we can actually counting within this grid, this unit area, and then we can counting those points, number of points inside that shapes. So that's actually there is a command function called the quadrat count. Yeah, we can actually, based on the first one is actually kind of a boundary window window object, and then nx and ny is a kind of a number of columns and rows to divide the grid. So 3 by 3 is the 3 by 3, 3 rows and 3 columns. So it is look like a matrix kind of a division kind of thing, and then we actually counting the number of points within each cell. Okay. Is there any questions so far? Anything? Okay. So if we can counting each number of points within each cell, we can actually do what is called the chi test for the discount, because actually when hello, oh my god,
That's okay.
Welcome back.
yeah, sorry about this, because my internet is, I don't know why my internet is unstable right now, but where you guys actually missed. do you did you hear the quadratic count parts and then the chi-test?
Yeah, so we heard you there.
Oh, okay. So I'm gonna restart about the chi-test one. So here, so assuming that we actually have a random, completely random, randomly assigned the points. In that case, in vice of the maybe the 3x3, and then our observation is the, I would say 27, for example. That means if we have a point is a completely evenly distributed, randomly distributed across the space, our expected value gonna be the 3, right? For the all cells, right? And then based on this one, what's the chi-test actually testing about is the how different they are for the each actual cell, actual observation of the points compared to this completely randomized point, unevenly distributed point, like a Poisson distribute. This one actually says about the Poisson distributed random points process, okay? Compared to this one, what's the variation or what's the difference from the actual observation? That's the what chi-test is about, okay? Actually, p-value is the kind of a 0.09. That means it is not the same. That means it is highly unevenly distributed. So that means it is not completely spatially random pattern. So there is actually some of the pattern identifying inside the actual observations. It is not the completely randomized kind of a pattern, like evenly distributed. So compared to this one to this one, chi-test actually does the actual observation is the completely randomized or there is actually clustering or dispersed pattern identifying the point. So p-value is the much larger. That means that there is definitely has a pattern behind these kind of points. That's how this one is actually testing about. Okay, here. Okay, so any questions? Anything so far? Okay, so this one is actually kind of a randomized. This one is actually kind of a quadratic count. Actually have counting the points of each cell, but the thing is, as you can see in this figure, depending on our boundary windows, each cell shape can be can vary, right? So that means we cannot actually standardize about the intensity of the points for the as a value. So to address those kind of a gap, the other way we can actually presenting about the density or intensity of the point is what is called the kernel shape, like calculating what is called the kernel density function. So these two is actually kind of a very good example about the kernel density function. So kernel density function is a more like a standardized value of the intensity of the points. Okay, so it is actually have a bandwidth gonna be clearly defined, and then depending on that bandwidth, we can actually get these kind of a heat map kind of a special point pattern. But how we can define those kind of a bandwidth is actually there is a parameter called the sigma, and then there is also a function called the BW digu. This is actually one way we can define about the sigma value. This one actually allows us to depending on our variation of the points location or point pattern, BW digu actually optimizing the sigma value that representing about the variation of the location of the points. So that based on that sigma optimize the sigma values, we can actually presenting or visualizing these kind of patterns like this. Okay, you can actually put it some of the number manually if you can have one, but BW degree is one of the methods that allows you to optimizing the sigma value that also allows you to representing or visualizing the point pattern as a heat map kind of a visualization. And also what I wanted to say is actually in case of this one, like a Dan one in the figure on the left, it doesn't have any problem to the kind of a bandwidth. What is called is there is a no actually have a edge effect gonna be happen. But in case of this one, like a Dan 2, or maybe if you have this kind of a shape polygon, and then there is actually point in here, like this. Maybe you can actually counting this unit, this very small cell, like a sigma value of the bandwidth. You can actually counting the density of the points per each unit area, and then you can actually start the visualizing the map like this. But the thing is, in case of these kind of edges, like the edges points, when you try to draw these kind of a small rasterized kind of a grid, there is actually, when you can see here, a little bit zoom in, is this is the boundary, and then there is a point, and then this one is actually out of the boundary, right? There is actually have an issue of what is called the edge effect. Okay, so in this case, there is also another technique how we can control these kind of edge point, which does not clearly mention into this chapter of the textbook. We actually thinking about depending on our polygon and then the points within that polygon, we also have to thinking about this kind of edge effect. Actually, edge effect gonna be happen when we actually draw the heat map like a Dan 2, like a circle size. When you're looking at these kind of edges, it is not completely kind of a curvy kind of a line. It is actually like a stair shape, like things like raster images. So there is definitely have these kind of edge effect gonna be happen. So there is several way we can control these kind of edge effect. And then depending on those edge effect kind of options, sigma value can be differently defined. So I wanted to say in here is, we also thinking about when we visualizing this kind of a special point pattern like a heat map, we also thinking about how we can control those edge effect. And also, depending on how we can control those edge effect, our modeling gonna be a little bit slightly different. Okay. Any questions? Okay, so at the bottom one, it is actually have like I said, it's obviously raster images, and then this one is just kind of how we can verify the areas, and then how we can try to develop the model. So whenever we have a define and then visualizing the outcome about the special point pattern, like this, and then we can actually develop the model like this. Like a PP2 is kind of a raster images of the point pattern, and then this gonna be the attribute actually attached to each point, and then we can actually developing the PPM is actually Poisson point model. Okay. What is the Poisson point model is it actually assumes that whenever you have a spaces, it actually assumes that all of the points and then the probability of the points gonna be generating within that space is the constant across the space. based on that assumptions, how our point pattern is the different, and then how those external variable like this variable can be explained that spatial point pattern like a distribution of points. That's what the model is about. Okay, and then what I'm saying is that this minus 4.05 is the, I would say, the exponential value for the minus 4.25. Okay, this is not the as a low value. This one is actually exponential value, like a natural value of the e minus 4.25. So it is very small density or stochastic value of the likelihood of the any random location within your boundary window. What's the probability of the points gonna be being generated in that location, and then how those distance measurement can be explained those pattern or those probability. In here, z value actually minus 6.06, which is highly significant. That means when you're looking at the actual point pattern and then a distance rest images, they are pretty similar. They actually represent the very similar pattern of the heat map. When you say above here, okay. So whenever you're looking at this one, compare this one based on the dist model, and then check out this one up to the den2. It's pretty similar, right? That means the distance actually explain very well, significantly explain the variation of the location pattern of the actual location point for the den2 in this case. That's how you can understanding about this model. Okay. And then 11.2 and 11.3 is another variation application of the spatial point pattern. 11.2 actually explains about whenever you have the point file like objects, it actually have a two-dimensional data with the Cartesian coordinates. You can actually try to do the ellipsoidal like a three-dimensional coordinate. They'll give you the answer error. So it is actually about the two-dimensional Cartesian coordinate, like a latitude and longitude, like a positive and negative kind of value in it. And also, when we thinking about the marked point pattern is, before in the previous chapter, we only cares about the location of the points, right? Like this. But the thing is, sometimes when we looking at the points, maybe I would say this one is actually like a car injury location, and then maybe X, there is another point for the X1. This one is actually car fatality, fatal death, accident location. In that means we have two different groups, or maybe more than two different groups, like a square, like a triangle. Maybe we can say about another type of the maybe bike accident point in this case. That means each point has the attribute. That's what is called the marked point pattern. Okay, so whenever you draw these kind of points table, there is actually have a location like a latitude and longitude, and then at the same time there is also attribute kind of a column in there attached to each point to carry. Oh my God.
Okay, we could hear you again.
Yeah. So can you see the screenshot? Can you hear the marked point pattern explained?
Yeah.
Yes.
Okay. Okay. So everyone understand what the marked point pattern is about?
Yeah, when you define
Okay.
a particular point and you assign it to something.
Yeah. Yeah. Actually, marked point pattern is the point with the attribute. Okay. So that's what is called about the marked point pattern. So in the previous chapter, we actually have only cares about the distributions or intensity of the point location. But oh my God, because actually, like I said, I recently moved to the new apartment, and then my internet does not settle yet. So that's how I actually using the kind of a hotspot services. So that's the reason why my internet is unstable. So I apologize for that. Yeah, I'm gonna set up my internet service next week, but I apologize for my unstable connection for the internet. Sorry about this.
What is this? This function as PPP. That what actually? Yeah. So assign an attribute.
Yeah, actually, as PPP s.tpp actually has a function that allows you to converting your data frame into the point pattern process object. So whenever you have a special database, like a special point database, SPPP actually allows you to converting that data frame into the PPP objects, so that you can using that data for your special point pattern analysis or special point pattern visualizations. Okay, that's the SPPP is about. And then whenever you have this one, you can actually creating about this hotspot or analyzing, developing the model like by using the PPM functions. And then this one is the spatial sampling and then a simulating kind of a process. Which one is a kind of a random sampling kind of a process, and then I try to analyzing about what's the density pattern is about based on your kappa or intensity value, and then it actually allows you to randomize your points within your special point pattern, or developing your model, or maybe some method. But this one actually, I don't know why others actually explained this one, because this one actually are not commonly used well, because this one is a totally kind of a hypothetical kind of a sampling process. So we usually do not use this one. Whenever we have a actual observation of the point locations, we actually visualizing that points as a heat map, and then we can actually converting those one is the PPP object, like a rasterized images, and also we can get another external variable, and then converting that external variable as another raster images, and then overlapping those things inside the model to analyzing the significance of the variation of the spatial location pattern depending on your external variable. And then chapter 11.5 is just kind of an example of the simulating the point on the sphere, like two-dimensional. But the thing is, whenever you have a kind of a sphere kind of a coordinate system, you can also have drawing some of the randomized point pattern analysis by using this kind of a sphere kind of a coordinate system. So this one is actually end of the chapter 11, but in the chapter 11, what you have to keep in mind is how you can develop the visualizing this kind of heat map, and then based on this map, how you can develop the special point process model is the key part of this one. So maybe I think I'm gonna try to show you maybe my example about how I can use the spatial point pattern, just briefly, because chapter 11 does not clearly explain about how spatial point pattern actually implemented for the actual analysis. So this one is my journal paper that I actually published a couple of years ago. And then what I can did here is okay, so as you can see here, there is actually location pattern. I actually geocoding all of these eviction location, and then you can visualizing this one based on the death sigma value, and then as a heat map like this. And then based on this one, I'm gonna try to finding about what is the other external variable that actually clearly explain about the variation of these patterns. So these are the possible candidates about the spatial what is called the covariates. So for example, when you're looking at this pattern, actually most of the eviction actually concentrated on this area, like downtown Salt Lake City County, right? And then as you can see here, maybe you can see, as you can see here, like a family below the poverty actually have a similar pattern. And also distance to the CBD also has a pretty similar pattern compared to my actual observation of the eviction. So that means we can actually think about is that these two are the very closely, significantly related with that spatial point pattern of the housing eviction. Based on that, we can actually do the model, and then these are the kind of a result about what's the significance. As you can see here, average distance to the CBD is the pretty significant, like negatively related to the intensity. So that means any location close to the CBD centroid area tends to have a higher intensity of the housing evictions. That's how this one actually interpreting about the result. So these are the kind of things, and then after that we actually try to do the model validation like this, and then we can say that this one is actually kind of following the very good needs of fit that actually validate our model, and then we can conclude my publication. So that's how these things work. So collecting the data, visualizing the kernel density mapping, and then collecting the external variable, and then making those variable as a raster image, and then overlapping our outcome spatial point pattern shapefile within that ppm function model, and then analyzing the result, and then interpreting it in terms of the intensity of the point location. That's how you can do for the spatial point pattern analysis. So that's the end of the chapter 11. So is there any questions so far? Anything?
Yeah, thank you. Can you put your article link in the chat, please?
Do you want to look at that one?
Yeah, is that open?
Okay. Hold on.
And also about the ppm model function. I have a question about that.
Yeah, these are the link for my journal publication, and then yeah, you can just look at it. Yeah, yeah, and then that's the kind of cause actually, as far as I know, my article is one of the very few pilot study that actually using the spatial point pattern analysis in urban planning area, especially for the analyzing the spatial pattern of the housing evictions. like where is the housing eviction gonna be occurred, and then what's the probability gonna be estimated or predicted based on my model. So that's the thing. So anyway, so thank you very much, and then I hope that see you next week then.
Thank you.
Yeah, bye bye.